In this video, we're going to talk about sequences. In the past, we've actually dealt with sequences, but we called them other things, such as slopes or constants. So in this example here, the prior lessons that you guys have done in the past, you guys have talked about what's called an arithmetic sequence. And so what makes this a sequence is that you're adding a constant number, or you're subtracting a constant number. So in this case, we're adding 5. And we've seen this before, for example, say in slope. We would add 5, or we would go up 3 and right 2 if we were graphing it. That's an arithmetic sequence. Now today what we're going to talk about is a geometric sequence. And the difference is we have a common multiplier. It could also be a common divider in the term of, like, say, a fraction. If the fraction's a half, it's really multiplying by half or dividing by 2. And we'll see that in a couple examples. So in this case, we can see if we add it, we would subtract 8, subtract 40. So we know that the arithmetic sequence isn't true. So then we look and say, okay, how do we go from -2 to -10? We're multiplying by a 5. Okay, how do we go from -10 to 50? We're multiplying by 5. So when you have this common multiplier, that's what determines a geometric sequence. So we're going to talk about this in a little bit, but essentially these are the two formulas for the two sequences. In arithmetic sequence, here is our formula. And don't stress too much about this, but that is technically the math formula for it. And then this is the geometric sequence, which we'll get to towards the end of the video. All right, so first, can we identify a geometric sequence from others? So in this case here, in example A, we have 120, 60, 30, and 15. So for it to be a geometric sequence, there has to be a common multiplier. And so if we look here from 120 to 60, that's going in half. From 60 to 30, that went in half. From 30 to 15, that went in half. Okay? So because we have half, that is going to be our multiplier. And since all of the ratios are the same, the common ratio is 1/2, and this is a geometric sequence. So again, a geometric sequence needs a common multiplier. All right, now in this example here, we go from 2 to 6, that would be multiplied by 3. From 6 to 11, we can't really multiply that. So because the differences are not the same, this is not a geometric sequence at all, because there is no common ratio where we can multiply it. All right. If we did the difference between these two, we would find out that this is 4, this is 5, this is 6. There is no common difference. There is a pattern involved in that, but it is not an arithmetic sequence. Okay, so hopefully you guys understand the difference between a geometric sequence and other ones. A geometric sequence, we need a common multiplier. All right, now, how do we extend this? Say you're given 4 terms and we want the next 3 or 4 terms. So what we do is we look here and say, okay, in example A, we have 3, 6, 12, 24. We want the next 3 terms. So we can create a table, which is probably the easiest way to do this. And we notice from 3 to 6, it multiplied by 2. From 6 to 12, multiplied by 2. So you would just continue multiplying these numbers by 2 until you get to the end of the desired sequence. In this case, they want 3 terms. So 48, 96, and 192 would be the next 3 terms. Okay. Now also keep in mind, in the directions, this is important because it says find each geometric sequence. So we know, again, geometric means we're multiplying it by a common factor. Okay. All right. Next, in this case, we go from 64, -16, to 4, to -1, and so on and so on. All right, now here's something important here. One of the math practices is looking for structure. So if you notice a sequence that's geometric, but it's alternating between positive and negative numbers, then the ratio is actually negative. So we haven't really seen a negative ratio come up too often. So when you multiply a positive by a negative, we get a negative. A negative times a negative gives us a positive. So that's why the ratio term in this example is going to be a negative. And we notice that we're dividing by 4 as we go through the ratios. Now, dividing by 4 is the same as multiplying by 1/4. Now remember, the negative is there because it alternates signs, okay? So keep that in mind. So from -1, if we multiply that by a -1/4, we get positive 1/4. 1/4 times a -1/4 is -1/16. -1/16 times a -1/4 gives us a 1/64. Okay. All right. So now let's graph a geometric sequence. Right. We can identify it. We can extend it. Now let's graph one of these things. So n in this case is going to be our traditional x value. So n is going to be the position or the order of which the number occurs. The term is going to be our y value, which we're going to call a to the n, and it'll make more sense in a few minutes. All right, so at an x value of 1, our term is 32. So we go, our first term is 32. First term is 32. Then we continue graphing. And study tip here, you're going to see that these are actually exponential. If you were to connect these lines, you would start to see it curve and create an exponential curve. Now, an arithmetic sequence is going to be a straight line. That's going to be more of your linear, where a geometric sequence is going to be more exponential, which is why we're covering this particular lesson when we are, because it's in the middle of our study of exponents. Okay. All right, so again, we come back to this formula, and we talk about a to the n. Over here is our y value. So what is a to the first? A to the first, in this case, is the first term of the sequence. So in this example, all right, the first term of the sequence is a1, which is 1. So our first term is 1. Now r is the position, right? R is the common ratio, and n is the number that we're trying to find. So in this case, when we look at our example here, right, this would be 1 minus 1. And that would give us 1. So this thing would cancel out. So our initial position is only left. Okay, so now our second term, it's 2 minus 1, which is 1. Okay, so then we would have 1 times 5. And in this case, 5 is our multiplier. So it's 5 to the first power. Why is it to the first power? Because it's 2 minus 1. Okay. All right, now the third term, this is going to be 5 to the 3 minus 1, which is 5 to the second power. So the initial term was 1, we're multiplying it by 5. So 1 times 5 is 5, 5 times 5 is 25, 25 times 5 is 125. So that part you guys get. Now the formula part might not make a lot of sense right now. So how do we get 3? Well, it's the fourth term, and we have to subtract 1. So again, fourth term, subtract 1 times our multiplier, okay? So, and that's how we end up getting this equation down here, okay? So really the two numbers that change again are the starting value and our multiplier. And then you can find any value in a particular given sequence, okay? So again, here's the formula. So they want, the first number is 2, okay? So again, 2 goes in for the A, and the common ratio is 6. So here's our two values, and they want you to find the 10th term. So now the 10th term is going to be for n. So 10 minus 1 is 9. So in the calculator, if you type in 2 times 6 to the 9th power. Now, when we do PEMDAS, for example, this would be the first thing we do, and then times 2. And you would end up with, I believe, 20,155,392. So make sure with your calculator you're able to get the same answer on this example using your calculator. If you can't, there's probably an issue on how you set it up in the calculator, in the order of operations the calculator created based on what you entered in. So please practice using your calculator to find the terms. All right, so say we wanted to find the third number in this particular sequence. So what we would do then is change this to 3, okay? So this would end up being 2 times 6 squared. Well, what is 6 squared? 6 squared is 36, times 2 would be 72, Okay, so that would be how you could find any number in the sequence if you're given the first term and the common ratio.